Right, we're now going to move into some rapid fire technical presentations. I'm very delighted to introduce the topic of perception as our first topic for our technical paper presentation. So starting off, we've got 3 talks for you, each 15 minutes long in this section. We're going to start off with nuts, NARS and speech from Dwane van der Sluis. Then we're going to come into addressing the unsustainability of deep neural networks with next gen AI from Amanda Vallentin. And then we'll have an adaptive vision architecture for AGI systems. We'll see if we've got any time at the end for any quick questions, but right now we're just going to rapid fire through them. And I guess you must be Dwane. Thank you, Dwane. Welcome. For microphone. What would you prefer? Probably this one, I would say. Let's get this. Thanks to everybody on YouTube for your questions. Yasanta, thanks for asking follow-up one about animal cognition. We will come back to you in writing in the YouTube channel if someone can quickly grab Tom with that one. But in the meantime, are you on, Dwane?
I might be on.
I've read your paper. I'm really looking forward to this talk.
Thank you very much.
Thank you.
Hello, everyone. Thank you. My name is Dwane. I'm here to present a paper, Nuts, NARS and Speech. So this is doing speech recognition using a system called NARS. NARS is non-axiomatic reasoning. So what is, if it's non-axiomatic reasoning, what is axiomatic reasoning? What are axioms? Axioms are things, facts we take to be true. A line is straight and goes forever. If we build a system up that way and try and code all human knowledge, as soon as one false piece of data is entered into the system, we can then prove anything arbitrarily right, correct, and wrong. So NARS is a different way, different approach. It can deal with conflicting information. It can deal with incomplete information. And also the particular software implementation is built on an assumption of insufficient knowledge and resources. So it knows it doesn't know anything, and it knows that it can't just have millions and millions and millions of training samples. So we've used this system for speech. Okay. So motivation. So our motivation was ONA, which is an implementation of NARS. Can it be used for perception and in particularly speech recognition? And then also we went further than that. Children at a certain stage of development can learn a new word with just 1 or 2 or 3 examples, and they've got that word and they can use it a week later. So can we be that sample efficient? I'm going to assume that the audience knows a little bit about NARS and ONA. I'm not going to really dive into that. You can treat it as a black box. I will speak a little bit about the input and output into it, but we can take that as, yeah, you have that. And also the NARSes, the language that we use. Again, I'm going to just go over that in quite a high level. The data set that I used was a standard speech data set, 35 words used to control robots, go forward, go back, stop, and then words that were deemed to be confusing with those other words. There were between 1,500 and 4,000 examples of each word. They were by different speakers. I don't know if you know much about speech, but it's less self-similar than you would expect. If I take the word one, and I get some recordings around here of people saying one, and we start doing correlations of those in the time domain, they're very uncorrelated. If we put them through a Fourier transform, which is, it's similar to what the cochlea in the ear does. We get stimulus into the ear, it starts firing different neurons in our ear, depending on what the frequency is that it's hearing. So that is then in the, what we call the frequency domain. If we take recordings of one, compare them in the frequency domain, they're similar, but they're not great. So this is actually speech is a strange beast, and it is quite a hard problem. So the high-level process was we take n samples of each one of the words, 2, 3, 4, 5, not that many. We encode them via some steps. We push them into Honor, which is open NARS for applications. And then we encode another word and then ask what word that is. Very high level. So the end-to-end process is take audio. The audio is recorded at 16,000 samples a second. So there's quite a lot of information. We then put it through what's called a MELD spectrum. So think of it as a fast Fourier transform, just pushes it into the time component with a frequency domain as well, frequency element, and then how much energy is in each one of those bins. That drops the amount of data down to 8,000 samples. We then generate a 8,000 by D random matrix, and we just hold this matrix. We just use that through one experiment. So we just generate a random matrix, multiply that by the 8,000 MELD spectrum, and end up with a very small amount of data, 1 times D. So 5 is for D. Like, so we can compress this down to just 5 dimensions. This is a deterministic process. We could reverse, we can't reverse it because we've lost information, but it's a deterministic process. We then encode those D elements in NARSes, which is the input into Honor, and then we run a preprocessor on it. You would have heard about duck typing. Like if it walks like a duck, if it quacks like a duck, it's a duck. Well, we've got something else here. It's a nullifier. It's part of Honor. And what it is if it's got 4 legs like an elephant, a trunk like an elephant, tusks like an elephant, big ears like an elephant, but it's pink, maybe it's a pink elephant. So this is it just gives it a little bit, 1 degree of freedom of movement, and it allows us to categorize things well. Never seen this animal before, but it looks like a, so that's the kind of thing that does. And then we pass it into owner. And then we ask owner, what is we encode all the words we've got, our database, and then we say, or 5 words, say, or 2. And then we say, what is this unknown word? If you'd like the pseudocode, I don't think we really need to go into that, but this is the same thing, as I said, the same process. Generate a random matrix, run through all these steps. This is what NARSes looks like. You don't need to know this, but it's just there. So what happens is for word 1, in the first of those, say, 5 reduced dimensions, I will call that, say, property 1, property 2. Property 1, and for one of those words, had 90% energy in that location, so I've encoded it as 90. The problem then comes to be if a word doesn't have a particular sound in a particular place. So 1 doesn't have a s at the beginning of it. So how do we encode that information? So if there's low energy at a particular frequency, I do it the other way around. I take the value off 1.0. So if if property 3 had an intensity of 0.2, I then make it to be 0.8 so that it's a strong knot, and the name of that property changes. We then run through the rest of the data set and ask what our class is. One of the caveats with this is that I had to run through all 35 classes asking owner if the unknown word was 1 or 2 or 3 or 4. So I think we can optimize this out, but this is at this stage what it had to do. Yeah. So what kind of performance did we get? So with as we vary the embedding size, so this is the small array that I take the data down to, at, say, when that is 5 elements, I'm getting 80% accuracy. This is quite good. As I vary the number of examples, just with one example, we can get 18% accuracy. This is far better than random. 3% would be random, is what we'd expect. rising up to sort of into 89 at 20 examples. A confusion matrix shows what's going on. The vertical axis is the input word, and then the horizontal is what we encode it as. Sometimes we can't get an answer. 0 is the word that others are most confused with. So the system will often say it's 0 when it actually isn't that word, which is curious. I'm sure there's, we could make some extra gains here. And so where does this stand compared to state of the art? So the state of the art on this data set is a attention-based neural network. It gets 94%, we get 89%. So, we're starting to, we're doing quite well, So, in open questions is there a magic best matrix, or can we just use any matrix as I do now? Can that matrix be found in a computationally efficient way? And then, so in summary, it's sort of nuts that just random dimensionality reduction. What we're doing is we're taking 8,000 samples, producing a random matrix, downsampling that to say 5 values, and we can push that through the system that it works this well. It is kind of very surprising. So, yeah, thank you. Are there any questions?
Great, thanks very much, Dwane. Great results there. Any questions? We've time for one quick one. We've got 2.5 minutes. Anyone? One here at the back.
Yeah, right. So I'm wondering about, like, I didn't quite understand. It's more like a clarification. So did you look at all the discrete steps of the time, or you looked at the malfrequency of the whole kind of recording of the command?
Did I look at all the data, or did I only look at the last bit? So no, I took the 16,000 samples Fourier transform down to 8,000 samples, matrix multiplication down to say five samples, 5 numbers, and that's all I looked at. I only looked at those 5 numbers.
Okay, thanks.
Yes.
Thank you very much. And big thanks to, unless there are any more questions in the room, we've got 2-3 more minutes if anyone does, or questions online. Here we go. No.
Thanks for the talk, Dwane. Like, how much reasoning is involved in the step between, well, gathering the data, well, whatever middle processing is going on, and querying? That's my question.
There is a bit. So the pink elephant was the majority of that. So what we started to do was compare 2 items that we know of, item to item. So we know about 5 words in memory, or 10 or 20 or 30 or however many it is. And then that preprocessor starts going back to the elephant analogy, does this look like an elephant? Does it look like an elephant? Does it look like a duck? But in this case, what word did it most look like? Yeah. And so then that did the pre-processing, then we asked, then that pushed that data into owner, and then we queried owner for what is the label of the word.
I see. Okay, yeah, thank you.
Okay. Good question.
Thank you, Dwane. Thank you, Neil. I've got one question in on YouTube from Digicar. Let me just say hello to Digicar. Hi, Digicar. Thank you very much for your question. Digicar asks, is this the only dimensionality reduction you tried, or were there others as well? And this was the one that performed best or well?
This is the first one that I tried that performed reasonably. There were other encoding methods that I was using via NARS and so forth, and I was trying to just downsample. I was trying to do many different forms of dimensionality reduction, but this is the first that worked, and then I couldn't beat it. So yes, thank you.
Fantastic. Thanks so much, Dwane, and let's give a big clap for Dwane. So this next paper is one I'm really looking forward to, addressing a really hot topic, DNNs and their limitations. And Amanda Vallentin in the room. Hi, welcome. Okay, switch that over. We don't have your sound back. Okay. Oh, okay. Thank you. Just having a 60-second technical break, folks. If anybody wants to stretch, stand up for a moment, get some water. I don't know if we have some water. Little stretch. I could run a yoga class. Have we any yoga teachers in the room? Yeah, that's right. Big stretches. We must have a yoga. Oh, where's Jay? Jay's a yoga teacher. Anyway. So sweet. It was good. I came from Amsterdam. Was it?
Yes. Oh, okay. I guess connecting to Zoom is advised. Like other on machine. Yeah, I guess usually they try and the organizer asks for the slides in advance so people connect to Zoom. You are the organizer.
Okay. Out of the loop. It's I'm out of the loop other than staying up last night, providing email addresses.
Okay. No, I mean, given that I haven't organized a conference, I perhaps shouldn't comment too much. I've been to enough that I've seen protocols.
No, I'm out. Yeah, my name's up there, but I'm like more the consultant.
This is new.
See, I don't have access.
Yeah, I guess someone should interact with
That's not.
That's because then alignment on all of the things from one
So you also find and everybody else also like creating There's too much chattering. You stay until
To Monday, like Monday afternoon.
so we're leaving on Tuesday. So yeah.
Are you staying in the same hotel? Are you in the?
No, we're a bit further away. We got the late booking. They were booked last week.
Yeah.
Still okay. It's like we bought the train and bus cards, so we're like riding on.
Daily cards. So
Yeah, so
the bus comes straight here, basically.
So I guess we'll do something.
Okay, if we swap the two
I was
sessions,
thinking
Robert's
that might be
ready,
a
and
good
then we
idea.
can keep it.
yeah, it's kind of a no particular.
Okay, people. Breaking news is that we are going to swap the order of these next two papers, and we're going to start now with an adaptive vision architecture for AGI systems with Robert Wünsche. So please give him a warm welcome. And Esther, you might go out and just tell if there are people milling around that we're starting again, please. Thank you. Welcome, Robert.
So now I have the honor to talk about this topic. Adaptive vision architecture for AGI systems or LHAI systems. So the motivation is basically a condition of all living beings that they operate in the real world, real physical world, not just the real world, which also includes the virtual world, but the physical real world. And a lot of animals and humans, of course, come with vision. And that's, for humans, one of the primary channels of perception. So that's, in my opinion, very important to realize this capability in artificial systems. Just because systems we are building or trying to build also operate in this particular condition. And state of the art in computer vision is that most contemporary vision systems lack learning at one time totally. Like we give the system, in the most extreme case, pre-labeled data, pre-labeled by humans, and so the human did most of the work by extracting the regularities from the environment, and then extracting the regularities from the raw perception stream, and then starts telling the systems with algorithms, this is a dog, this is a cat, and my opinion is that this is not the way to go at all. So they lack learning at one time, and yes, it has to happen at one time. Yeah, I scratched the requirements of intelligent systems. So they have to be so it has to be open. So with systems are closed, so they are not open to learn anything new. And they also must be able to operate in under the finite resources. So finite memory and finite cycles under the processing. And it doesn't really matter how the processing is done for this requirement. So, and there are different types of this finite requirement. And the most extreme case is if it's operating on the assumption of insufficient knowledge and resources. And a less extreme case is if it's operating just under finite resources and bounds. And for these systems, inference time is bound because it has to happen in real time. So it's not an option that a system takes time X for the first frame and then a bit longer for the next second frame and so on. So I've also scratched this, what's wrong with retraining everything, lack of adaptation. So we also make the distinction between learning and adaptation. Adaptation is a bit more extreme form of learning to some of us. So the problem was an implementation of a vision system which operates under these conditions. So then the engineering question is how to do that. So then I came up with an architecture where the raw information perception stream is converted to grayscale images. This has the advantage that it gives us some form of generalization because the same color might map to the same grayscale information, and then this is then fed into a convolution, and the output of the convolution is then fed into a neural network, which is trained with a particular objective. But one of the key parts of this architecture is a proposal generator. And then the information flow is from the proposal generator and the neural network to the classifier, which just spits out symbolic categories. And the classifier is based on a prototype mechanism. So now how do we get proposals from a raw stream of perceptual data? So one of those assumptions is that the raw stream is segmented into frames. So there is a current frame and the last frame. Then we compute the optical flow from these two. Then this is fed into an algorithm to extract bounding boxes by clustering. And yes, the output is then the bounding box, and the extraction of the bounding boxes is done by detecting the optical flow, then clustering it by the optical flow into let's call it buckets. So the idea is that the pixels with the same motion on the same bucket. So then the bucket is grouped, and then we get bounding boxes from that. Now we come to the neural network. So the purpose of the neural network is to transform the raw perception into a more abstract representation, which is a real valued vector in this case, in this architecture. And the requirement of the neural network is that the requirement of the system is that it's able to learn classes or categories at one time for unknown classes. So there is no designer which decides this is a car, this is a table, and so on. And another requirement is that similar inputs should map to the similar categories. So one engineering issue is then how to learn the parameters of the neural network when we don't know the encountered classes or categories or at one time. So one solution which I selected was to learn the parameters of the neural network with the help of the Siamese neural network objective. So the objective on the learning time of the neural network at the design time is the Siamese neural network objective. And then we optimize for the distance between the vectors of the output of the neural network. So that similar categories have a small distance, so 0 or something close to 0, and not so similar has have a high distance. And the hope or requirement is that this generalizes well enough to unseen objects at one time. And it's inference time for the neural network. So yes, this is a slide where which I've talked about already. So at design time, training time of the neural network, we duplicate the parameters of the neural network, feed in training example with one label into the first network, and another training example of the same into the other network. Then we get a real valued vector from each network. Then we compute the distance, and then we have a distance which we can optimize for with an optimizer. With machine learning machinery. So we get then a mathematical function in the neural network, and the intuition of that function is that it spits out a vector for any input, and the hope is then that that output is hopefully similar to the output we get from the same class, which might look the same or might look completely different in the input. But there can also be cases that there are clusters of the same category, and then there are clusters of the same category for human, but which land in another part of the space. And in my opinion, this isn't really an issue, because if the system encounters, let's say, category which is here and does then something, and then reacts to and then perceives some response from the environment, then it can also learn that it's doing something which is a reaction from this, leads to the same thing. So that's that. Now I will talk a bit about the classifier. So the purpose of the classifier is to take the continuous space and map it to a discrete let's call it symbol, in the output. And this classifier also has to operate under a finite time because it's a real-time system. And it can also not allocate more and more memory over the lifetime of the agent, because then it would potentially allocate unbounded amount of space, and this is a no-go. And this is implemented with a set of prototypes which are mained, and the bound of space is maintained by removing items which are not important, either because they're not anymore encountered in the environment, or because there are too many items which push out old items and so on. Now I come to a demo. So the system we're talking about starts from scratch if it's restarted, if it's started, and then it's always room to pick up new categories. So here we see the work of the proposal generator. So there was the last frame, and this is now the current frame, and it instructed the bounding boxes here by the motion of the car. So that's that. And now when I give the system resources, and it recognizes the motion, builds the bounding box around the motion, and categorizes the pixels in the rectangle. And it also works for motion which is moving against each other. So that's that. And here we see the inner workings of the system, distance and similarity. And this is then the debug output of the classifier. And in this case, it has created already this many categories and recognized so many instances. And now if I restart it, it starts out from scratch, knows nothing at all. And yes, it knows nothing, so 0, 0. And yeah, and if there is a motion, then it again builds up the, then it finds the motion, identifies the category and so on. So that's it.
Just thinking, I'm on. We have time for one quick question in the room for Robert, or one online. Here we go.
Yes.
Hi, my name is Michael. Have you tried this on more than just this particular type of training set, like where objects are in 3 dimensions moving forward, closer and further away, so that the size changes?
Not yet,
okay.
but the size change should be handled by the proposal generator, because if it's far away, then the motion is like in a small bounding box, and if it's near, then the motion is in a large bounding box, so it's sort of handled. Okay.
Thank you very much. Loads of pics of me and introducing a woman, please. Right. Delighted to have Amanda on stage. Robert, we need your microphone. Thank you. Brilliant to see talented women coming through in the field at our AGI conference today, and really essential and important topic for us now. Okay, everybody ready online? Welcome, Amanda. Thank you.
Thank you. Yeah. Okay, I'm online. This is great. I'm really excited to be here today, especially in Sweden. We all know Sweden as the hometown of Greta Thunberg, and she's a great inspiration for me personally. And today I'll talk to you about sustainability challenges of deep neural networks, and I'll talk about their limitations and bring in real world examples of where we've tried to implement deep neural networks, but they don't work exactly as expected. Yes. So let's start with what we know about their environmental impact. So if we look at large language models like GPT-3 and Bloom, there's been some attempts of measuring their footprint. And the way we've done this is by taking the power consumption they had in the final training phase and converting that to CO2 equivalents. And if we compare GPT-3 and Bloom, we see that GPT-3 has a footprint of 502 CO2 equivalents, where Bloom only has a footprint of 25. And so this is a pretty big difference. And this is actually due to where geographically the models were trained. Because since US has less renewables than France, GPT-3's footprint is much larger. But it's important to realize that when we only look at the final training phase, we only see a fraction of the full environmental impact. So we need to look at these models in a life cycle perspective. And if we take GPT-3's impact of 502 tons, what's not included in those calculations is the whole impact from the hardware we use to train and deploy the models on. Neither even in the development phase, we don't have tuning of hyperparameters included, which we also know is a very energy intensive process. And if we compare how little we know about these models to a car, it would be like only knowing the impact of building the engine. And this is pretty concerning because already this fraction of their life cycle is already equivalent to about 9 petroleum cars, the impact of those. And here we're including the entire life cycle plus the fuel you would use for these cars. With deep learning networks, we also can see some impacts on inequality. When you need to build and deploy a deep neural network, you need access to extensive amounts of data, you need access to some very heavy duty hardware, and you need access to electricity. And all these assets are expensive, and this will limit who has the resources to build and use these technologies, which especially for smaller and medium-sized companies, they will not be able to afford using this technology. And we also know that a lot of these models have bias in them. For example, dermatology, deep learning models used there for skin cancer detection, they only work for white people because people of all color were not represented properly in the training data. So there could be a possible discrimination of races in healthcare. Yeah. So deep neural networks also have some limitations to what tasks we can use them for. And because they have a simplistic and static understanding of our world, they're not capable of inferring simple relations, and that makes them not able to do reliable reasoning. And therefore, any task that requires reasoning, we should be very reluctant to use deep neural networks in those tasks. Also, when once the neural networks are deployed, they cannot learn anything new autonomously. A human always has to interfere. And this makes it very challenging to be a developer, because as a developer, you need to make sure that all the scenarios that the model will see once it's deployed is also present in the training data. And this is probably also why we haven't seen fully self-driving cars yet. And if you think about it a bit more, you can actually compare a deep neural network to a dodo bird. And it's because, like the dodo, deep neural networks are very sensitive to any changes in their habitat. Meaning that, you know, if the data they meet when they're deployed is too different from the training data, they die out. And yeah. So a use case that's often emphasized for deep neural networks are radiology. And we probably all heard the phrase, AI will replace radiology in XX years. And naturally, I was a bit curious if that was the case. So this spring, I did a research project where I interviewed a chief radiographer at a Danish hospital that had been involved in buying AI solutions for a large region in Denmark. And she told me that they're very reluctant to invest in any more AI solutions, because they've already seen that it's been a loss-making transaction in the few cases where they've done it. And by that, I mean that the AI models ended up being more expensive than the radiologist that they were supposed to replace. And another challenge is that the companies that sell these models, they won't take legal responsibility for the predictions. So that puts the radiologist in a dilemma, because how can you trust a model when it's your name and it's the patient life that's on the line? And that leaves very little room for any saved resources, because the hospitals, if they invest, they need to see some kind of, it needs to be a viable economic decision. And if they have to, instead of only having a radiologist, they also have to have a radiologist and an AI model, then they're not able to invest. And so right now, deep learning models are too expensive to do radiology any good. And yeah, so I just want to end my presentation by saying we should be very aware of the limitations of deep neural networks and what we use them for, so we don't end up wasting resources, deploying them in environments where they won't do our society any good, because they do have a large environmental footprint that we only know a little bit about. And because we also know it's very expensive to build these models, and there can be bias that affect minorities negatively, we both have a technology that compromises environmental protection and social inclusion. And this is a big red light for sustainability. Yeah, so yeah, thank you for your time.
Thanks so much for that, Amanda, and you've admirably caught up a few minutes of the time that we've left behind. Who's got questions for Amanda in the room, please? Dun, dun, dun. Come on, somebody.
That was really great, and I agree with a lot of these points, but some of them seem very transitory, like, you know, they're catching up at reasoning, and it turns out that the Azure data center that GPT, 27 is trained on is co-located with a hydro dam. So I guess I'm wondering, like, what's your view of which of these will still be relevant in 5 or 10 years as opposed to like just right now?
Like what models will be relevant? Or?
Which of these factors that we have to
Oh,
worry about?
I would definitely say the energy consumption of the model development. And I also think, like, in general, we need more information, especially on the hardware part. Like, what is because when I don't think we can have neural networks that don't need very heavy duty hardware to be trained. And like, because the hardware has all these metals that needs to be mined, and some of them are very rare as well. We don't have that many of them in the world. Like, I think that impact is very important to be considered as well, even if neural networks do end up being capable of doing reasoning and stuff. Like, maybe it might be worth looking into other architectures that can do the same but with a lower footprint.
Super, thank you so much indeed. 2 more coming in. Name and question, please.
My name is Artem. Thank you for your speech. It looks like in post-AGI world, it is inevitable that almost all our cognitive workload will be transferred to data centers and other computers on the edge, mobile devices, and we will, as a civilization, will have high level of energy consumption related to our cognitive AGI workload. What you can say about this?
Like the growing energy consumption. Yeah, it's so right now our total like our demand from energy is only rising. Like, for example, the entire transport sector, they used to run everything on oil, and now they have to convert to electricity. So it's going to be very interesting to see in a few years how we get over this challenge or solve it or deal with it, because yeah, you can put up a bunch of windmills, but we also have to make sure that those windmills can account for the growing energy demand. And yeah, and to be honest, like the renewables, they're also a bit unreliable, and they're also expensive, and they're not free to set up. You also need to develop the infrastructure further. So it will be interesting to see if we have the energy prices will just rise incredibly. Yeah, and how maybe we need to think about what's ethical to use our energy for in the future. Yeah.
Thank you. We've gotten a question from the YouTube audience. Thank you, Clickerico, if this has been copied correctly. If GPT-3 training phase is equivalent to 9 cars' life cycles, even scaling to the whole process, that doesn't sound like a lot, does it?
Like 9 cars?
Yeah, was that correctly? Has he correctly interpreted your slides? If GPT-3 training phase is equivalent to 9 cars' life cycles.
He doesn't think that sounds like a lot.
Yeah.
Yeah. Yeah, it's the same with my boyfriend down there. We've discussed this, but I think, looking into a world where energy might be as far as source, I think it's very important to just think, okay, what value does it bring to our society? And yeah, maybe he is right. Maybe it's not too bad, but I think that my point with this slide was that we only know a fraction of it, and that is worrying.
And that's just the final training phase.
Yes.
As you say, not including the whole life cycle. Great question, Glickerico. We have 2 more quick questions in the room, I think, and then we're going to go to break. Sorry, 1 second, and then back to you afterwards.
Thank you.
Hi, I'm Renato. And first of all, thank you so much for your presentation. It was amazing. Yeah. Do you have any thoughts on the possibility of, for example, a decentralized community of people training neural networks, so that at least the main architecture is not in the hand of like super big tech companies, but is an environment in which anyone with their home computer can connect to a network and be part of the development of a generative model like ChatGPT.
Yeah, I think that would be great for the computer science society, that more people learn how to code and can build these models by themselves. But I would be, you know, a bit concerned with yeah, the environmental effects if everyone can will start these very energy intensive processes on their own computers. Like, what will it add up to if everyone does the same? Yeah, so I think it's also, you know, kind of like learning and resource consumption, a trade-off between those. Yeah. Yeah.
I'm Emil. I have a question to this one. You mentioned that the issue of deep learning is that it's not learning during inference, during the prediction when we using that.
Yeah.
Is it not like double-edged sword that when we start learning our model during the inference, there is no control what we teach this model? And for example, we have medical model, we teach it and we reliable that results are stable. And then during the inference, we are starting teaching it something. And after, I don't know, a few years, it will predict something completely different, which is not stable and not reliable. So from my perspective, I think that we cannot train model during inference is something what make it stable and reliable that we can use it.
Yeah, I mean, I think it's still a case of you know, finding those use cases where it's okay, where you that it doesn't learn anything when it's deployed. Yeah, so yeah, because then there's nothing wrong with the way it learns. If it's in a more controlled environment where it can be taken down and corrected in a sense. Yeah. Yeah.
Thank you very much indeed. Big round of applause for Amanda.